Electronegativity and bond polarity. We've talked about electron affinity, and it's easy to get that confused with electronegativity. So we're going to explain electronegativity now. So the Lewis model is a very simple model, and just drawing electrons as dots is obviously a drastic oversimplification. We've talked about quantum mechanics, and we know that the electrons are actually this like standing wave around the nucleus, and it's all very complicated. And here we are just making dots out of them. The electrons that are shared between two atoms are not always shared equally. There's sometimes an unequal sharing, and you've probably experienced this as a kid. You know, you and your brother are supposed to share this cookie, and it gets broken, and one half is much bigger than the other half, right? Yes, we shared the cookie, says the older brother, but it wasn't fair, right? When atoms share electrons, it's not always equal sharing. And I think of it this way. This is, another thing that happens in chemistry land. So here's hydrogen. This is the hydrogen household, and here's the fluorine household. And they each have a little boy, the electron, that's being shared. Those two electrons are going to go out and play together. And you might think, well, they'll probably, spend some time at hydrogen's house, some time at fluorine's house, and they'll go back and forth. But hydrogen's house has an old black and white TV and a VHS video player, and they only have some old Bernie videos. And if you're hungry, you can get a cup of water from the tap and some saltine crackers. But over at Fluorine's house, they have a big screen TV. They have a swimming pool with a slide in the back. They have a soda fountain in the kitchen. And if you're hungry, Mom will order pizza to be delivered, any kind you want. Where are these kids going to spend more time? At Fluorine's house. Why? It's awesome, right? It's more attractive to the little boys. Okay? So, fluorine is more attractive to electrons. And so, this pair of electrons that's being shared between hydrogen and fluorine is actually going to be more towards the fluorine than the hydrogen. The fluorine kind of hogs the electrons, and hydrogen loses out a little bit. Here's a picture down here of the electron density. And we see the electron density, it's lopsided. It's more towards the fluorine than the hydrogen. What that causes to happen is because this pair of electrons is spending more time over here than over here, the fluorine end of that molecule is going to be a little bit negative. It's not an ionic compound. It wasn't a transfer of electrons. That would be the fluorine household, the fluorine family adopting the child, right? He no longer is a hydrogen electron, he becomes a fluorine electron. That would be an ionic compound. They're still sharing. The electron still belongs to hydrogen, but they're not shared equally. And so this end is a little bit negative, this end is a little bit positive, but it's less than a whole plus 1 or minus 1. And so we use the lowercase Greek delta to indicate that this is a partial positive charge and this is a partial negative charge. And it could be pretty small, it might be only like a third or a fourth of a charge, right? It's just a partial charge. But it's still important because when you take this hydrogen fluoride molecule, if you look at them just in random space, they're going to be oriented randomly because it's a gas and they just twist and turn all over the place. If you apply an electric field, a negative plate here and a positive plate, all of a sudden they'll line up like little magnets. The negative end is attracted to the positive plate, and the positive end is attracted to the negative plate. This is a polar molecule. You think of the word polar, what do you think of? Bare and north and south, right? The North Pole and the South Pole. What's different about them? Penguins and polar bears. Magnetic fields, right? The North Pole is at one end of the Earth, and the South Pole is at the opposite end. You can't really have an end of a sphere, but they're on opposite sides. And the magnetic field of the Earth is different at the North and the South Pole. So a polar bond, now we have different ends of the molecule. One is slightly negative, one slightly positive. You put them in an electric field and they act like a compass, and they'll line up with the electric field. Another designation we use is this arrow. So there's a plus at this end of the arrow, and then the arrowhead over here. So this is the positive end, and this is the negative end. And I think of this as the neighbor out on the street. One of the moms comes out and says, or the dad comes home, and is like, where are the boys playing today? And the neighbor points. They're over there. They're at the Florian's house. Okay, so the arrow points to the side that the electrons are at more often. Any questions?
What exactly are those little signs that are right?
These little guys, that's the lowercase Greek delta. So a capital delta is the triangle that represents difference in or change in, and the lowercase Greek delta looks like a D with a poor posture or something.
Hershey's Kiss.
Or a Hershey's Kiss, yeah, depending on how hungry you are. Yes?
So the electrons, they usually go more towards the element that has the higher electronegativity?
Yeah. Electronegativity, we'll see in the next slide, is how much attractiveness an atom has for the electrons. So electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. Electron affinity was the energy change when an electron is added to a neutral atom to make a -1 ion. So there's some similarity there, but the concepts themselves are actually quite different. Electronegativity happens only in a covalent bond. We find that this electronegativity is inversely related to atomic size. Fluorine is the most electronegative element. The noble gases are so unreactive, some of them form no covalent compounds at all, and so we just completely ignore the noble gases when we talk about electronegativity. So they're just left off. So we can look at a graph like this. So here's the periodic table, and the height of each of these columns represents the electronegativity of that particular element. We see there's a general trend. As you go across, the electronegativity increases. As you go down, it decreases. Yes?
It looks like Game Cubert.
It does look a little bit like Cubert, yes. That's an old one. Forgotten about that one. Hydrogen over here seems a little out of place, doesn't he? But isn't he always?
Yeah.
Hydrogen's always just got to be an exception to things. The trends, the trends are not absolute. We see that there's kind of a hump here and then it goes back down, but there's a general trend. So it's the opposite of the trend in atomic size. Atomic size decreases as you go across and increases as you go down. And we talked about Coulomb's law and how the attraction is greater when you have a smaller atom because the distance is less. And so that might be one way to think of it. These numbers, the person who originally developed, I think it was Pauling actually, he said, well, let's just make the most electronegative one 4, and no electronegativity would be 0. And so these are all just relative numbers, kind of randomly assigned on a scale of 0 to 4.
So it's like a GPA?
A little bit like your grade point average, yeah.
Radium's dropping out.
Fluorine is nailing it, you know. And so the way I remember electronegativity trends is fluorine, which is kind of counterintuitive because F in a grade point would not be a 4.0, but fluorine is the most awesome. And so as you're going towards fluorine, you know, if you're comparing bismuth and phosphorus, well, you'd predict that phosphorus is more electronegative because he's closer to fluorine. So all the trends increase towards fluorine. Yes?
Why are there no noble gases?
There are no noble gases because they're so unreactive that we don't even include them.
Is that why when we were talking about hydrogen, how because these gases are so unreactive, like if hydrogen was by itself, that's when it explodes, like just in air, but you put, I think you said xenon or something in it. The noble gases will not burn. They're not combustible. There are many other gases that won't burn either. Nitrogen doesn't burn. But hydrogen
in air will combust. It's quite reactive. But the noble gases are just so unreactive. I mean, if you can't form a covalent bond with another element, then there's no way to measure an electronegativity. So they're just left off the table. It's okay, they're not offended. They're just so cool and happy in themselves, they don't care. So polar bonds involve unequal sharing. Of course, there's degrees of unequal sharing, right? There's just a little unequal, and then there's a lot unequal. And so the degree of polarity will depend on the difference in the electronegativity, and that's often represented as delta En. So the difference in the electronegativity. Electronegativity is a really long word. We get tired of writing it. So capital E, capital N. So we can go from a purely covalent bond. Your book uses the word pure covalent. I prefer the word nonpolar. I think it's a little more descriptive. Nonpolar covalent bond where the electrons are shared equally. And so we need to have some divisions here because we can go from the ionic bond where the electron's transferred, somewhere in the middle it's shared unequally, and here it's shared equally. You kind of have to decide, well, how equal is equal, right? You know, if you cut a piece of cake in half and it looks the same, both pieces look the same size, do you call that good enough and say that's equal? Or do you get out a scientific balance and weigh it and, oh no, this one's 0.003 grams more. This isn't fair, right? Doesn't really matter. So we've made some arbitrary divisions. If the electronegativity difference is 0.4 or less, then it's considered a nonpolar bond, shared equally. If it's between 0.4 and 2, then we say it's a polar bond. And above a difference of 2.0, we say it's an ionic bond, that essentially that electron is transferred.
Can we go back to that real quick?
Yes. You may need to refer to these divisions, the 0 to 0.4 and the 2.0, to answer some of the homework questions. And if you do that, then you need the table of electronegativities, right? So if we wanted to know if a carbon-hydrogen bond was polar or not, we'd have to look at the table and see that carbon is 2.5, hydrogen is 2.1, the difference is 0.4. So we say, well, that's essentially a nonpolar bond.
You just take the difference.
It's the difference. It's the difference in electronegativity between the two atoms that are bonding. So it's good to know how to do that, but most of the time, we just need more of a ballpark idea. Is this polar or not? And so what I want you to be able to do for an exam is just to be able to look at the periodic table and say, these are polar bonds or not polar bonds. I should write this somewhere. So this is, the sketchier rule of thumb. So nonpolar, identical elements. So if you have two hydrogens bonded to each other, it's a no-brainer. They're the same element. The difference is 0. They're going to be nonpolar. If you have a metal and a nonmetal, oops, that's not how I want to do it. An ionic bond, you've got a metal and a nonmetal. So if you've got sodium and chlorine, there's really no need to look at the difference in electronegativities. A metal and a nonmetal is always going to end up being ionic. And then the polar covalent. Not always true, but mostly true. Two different nonmetals. I can't think and write at the same time. That's a problem. Two different nonmetals. So if I said, well, is a phosphorus-oxygen bond polar, nonpolar, or ionic? Your best guess is polar because they're two different elements. Okay? Now, if you really wanted to know for sure, you'd have to look at this table and look at phosphorus and oxygen. 3.5 2.1, so the difference is 1.4, yeah, that one's polar. There are exceptions, of course. Carbon and hydrogen would be nonpolar. Nitrogen and chlorine, they have the same electronegativity, they're nonpolar. But most of the time, these rules are going to work. And you don't need a table or anything to look at. Yes?
So what if you had a metal and another metal?
It's going to be a metallic bond.
Oh, okay.
Yeah. Another way to measure bond polarity is with what's called a dipole moment. And this is abbreviated with Greek mu. And this occurs anytime there's a separation of positive and negative charge. So in a polar bond, you have a separation of positive and negative charge. So the dipole moment is equal to Q, which is the magnitude of the charge, and R is the distance between them. And the unit that's often used for this is the debye, a capital D, and it's equal to 3.34 times 10 to the minus 29 coulomb meters. This is something that's not going to come up on an exam either. It could show up on homework, but you need to have at least heard about this stuff, right? Sometimes, you go on to a later class and they start talking about something like this and you go, well, I don't remember that exactly, but I heard about it and I kind of know this is where I would go to look it up and figure out what it is. So that's kind of what this is. So for chlorine molecule, the difference in electronegativity is going to be 0. The dipole moment is also going to be 0 because that charge magnitude is 0. Chlorine and fluorine, that would be chlorine monofluoride. They have an electronegativity difference of 1. Is that going to be polar or nonpolar?
Polar.
Polar. And the dipole moment is going to be 0.88. So dipole moment is just a more sophisticated way of measuring the degree of bond polarity. For lithium fluoride, we can look at this formula and predict that it's ionic because lithium is a metal and fluorine is a nonmetal. The difference in electronegativity is very high, 3.0, and the dipole moment is really, really high too. Another way to look at this is what's called percent ionic character. So with an ionic bond being a complete transfer of electrons, how close to that ideal is this particular bond? So we're comparing the bond's actual dipole moment to the dipole moment if the electron was completely transferred. Now this is going to bother some people. No bond is actually 100% ionic. So I've been telling you that in an ionic bond, an electron is transferred from one to another. Not exactly. Mostly transferred. And it's a little hard to understand, well, how can you kind of have it? But in essence, in practicality, it's transferred. So what we consider an ionic bond is something that has over 50% ionic character. So here's a graph of some compounds. Percent ionic character versus electronegativity difference. Anything that has a percent ionic character above 5 is going to be considered an ionic bond. And if we look at all of these guys, they're falling into this category of electronegativity difference being 2. Some of these are a little less than 2. So these are considered ionic by the percent ionic character. But all of these guys are ionic. And if you look at them, they're all metals and nonmetals. Then there's this guy over here. He seems to be hanging out with this group, but his percent ionic character is less than 50%. And so hydrogen fluoride, metal-nonmetal, is not considered an ionic bond. And down here, all of these guys, metal-nonmetal, they're non-ionic. Any questions? Where would H2O be on that graph? Well, all of these are diatomic molecules, where we're just looking at the bond between, the whole molecule is just 2 atoms. So you'd have to look at the bonds in a polyatomic molecule separately, but the hydrogen-oxygen bond would be somewhere under the 50%, because it's definitely a covalent bond. So this is the sort of question that you should be able to answer on an exam. Determine whether the bond formed between each pair of atoms is pure covalent, polar covalent, or ionic. So, iodine and iodine, nonpolar or pure covalent. I like nonpolar better. Nonpolar or pure covalent. How about cesium and bromine? Ionic. Because we have a metal and a nonmetal. How about phosphorus and oxygen? Oh, I accidentally used that earlier. That's going to be polar covalent. Most of the time, if you have two nonmetals, it's going to be polar covalent. There are some exceptions, but not too many. Any questions?
So say if like something like this were on the test and the question was like for one of those exceptions, how would we know? Or would we
I wouldn't try to trick you by putting an exception on there. Because an exception would be carbon and hydrogen. That's an exception that I would recommend that you remember because in organic chemistry that comes up a lot. But at this point I wouldn't expect you to know that, but this one is a nonpolar. If I give you the table of electronegativity values, then you should know that carbon and hydrogen is a nonpolar bond. Any other questions?